Hi everyone. So my presentation is going to be on the ion trap quantum computers. So what I'm going to do is I'm going to compare classical information versus quantum information, and I'm going to talk about how the ion trap works, how we implement quantum computers with the ion trap. The fundamental unit of information in computer science is known as the bit. A bit can be be in a state of 1 or 0. You can also think of it as true or false. Classical and quantum computing are very different. Quantum computing is probably not a likely candidate to replace classical computing, but they may be able to complement each other. So we're going to compare bits and qubits. So in a classical computer, a bit can only be a 1 or 0. If you have a transistor, the transistor can, for example, just be low voltage or high voltage. It can't be both. But we know that in classical mechanics, a particle can be in a superposition state, which is its wave function. Right here we have spin states. Upspin is a 0 and downspin is a 1. If you have a superposition state that is 50% 0 and 50% 1, it's represented right here, and that is our qubit state. So in general, when you have a qubit in the superposition state, you can represent it by alpha times that 0 state plus beta times the 1 state. The magnitudes of alpha squared and beta squared have to add up to 1. Alpha can be thought of as the probability of extracting a 0, and beta can be thought of as the probability of extracting a 1. So for example, if you want to encode a 1, you might put the superposition state as 60% pointing in the 1 in the spin down direction. So that would give you a higher probability of extracting a 1. So in a classical computer, in this example, we have 4 bits. The 4 bits, since it's classical, it could only be 1 or 0. So even though these 4 bits have the potential of encoding up to 16 different states, it could only be at one state at once. So this state is currently in 0, 0, 1, 1. And if you want to do another state, you have to change the bits of one or more of those bits. For a quantum computer, if we have 4 qubits, since we have the power of superposition, and it could be in all these states at once, you can encode all 16 states at the same time. And then these qubits are entangled with each other, and because they're entangled, they can all be in all these different superpositions at once. So one of the ways we can compare a classical and quantum computer would be, for example, how they search a series of decisions. You can think of this as maybe searching through a map. The classical computer would have to search every single path one at a time in order to find the optimal route. A quantum computer is in superposition, so it can search all paths at the same time. So in that example, the quantum algorithm only had to take 4 steps to find out the optimal route. But the classical algorithm would probably have to take many different paths to find the optimal route. There are many different quantum computer models. There's the ion trap, which is the one we're going to talk about. There's polarization of light, Bose-Einstein condensates, which are right here, quantum dots here, fullerenes, there's a fullerene right there, and the adiabatic quantum computer, which is the one that D-Wave currently makes. But we're going to talk about ion traps. Here's a representation of an ion trap. So in an ion trap, what is going on is that we're using dynamic electric fields to confine a group of ions in all 3 directions. So here's a little video of an oscillating magnetic field. The magnetic field is oscillating and it's containing the ion in the middle right here. These the electrodes of this ion trap are hyperbolic in shape and they oscillate. They have an AC oscillation. And so when they oscillate in one direction, they pull the ions in the horizontal direction. And when the AC field switches, then it pulls them in the in the vertical direction. So this right here is the differential equation representing, it's the equation of motion. It's a harmonic motion. It's the equation of motion for the ion. So when we're doing an ion trap, another thing we want to do is we want to cool down the ions. And the reason why we want to cool them down is because we want them to be in a we want them to be in a very stable quantum state. And stable quantum states can be achieved if you have very low temperatures, probably close to absolute zero, down to the microkelvin scale. And this is achieved with lasers. And so the way it works is when you want to set your laser to a wavelength of light that is higher than the absorption wavelength of your ion. So when the ion is stationary, as in one right here, the from the ion's point of view, the laser light is the wavelength is too large, so the ion does not absorb the light. Now, when the ion is moving in the same direction as the laser light, from the ion's point of view, the laser light appears redshifted, and this redshift is not the right wavelength, so the ion does not absorb it. But when the ion is moving in the same direction as the laser light, from the ion's point of view, that laser light is blue shifted. So because they move in opposite directions, the ion absorbs the laser light, and so it absorbs the energy, and because the photon has a momentum to it, the ion is slowed down. One thing that they like to do is they shoot the ions from many different directions. So here's like 6 different directions, and you do that so that you can make sure that the random motion of these ions is slowed down. So every possible direction of velocity is countered with a laser light, and you're essentially trying to make them stand still. But of course, because of the uncertainty principle, the ions are never going to be confined to a single space, and they're always going to be a little bit of jiggling around. But they've managed to get them down to the micro Kelvin scale. And so in this study from Duke University, what they did is that they used a particular ion. They used the calcium 43 ion, and they used it to develop an ion trap. So the reason why they use the calcium ion is because they say when they applied a magnetic field of 146 Gauss, this magnetic field generated hyperfine ground states. Well, these hyperfine ground states were separated enough so that that they're not affected by the magnetic field, and we want this because we want the states to be unaffected by the magnetic field because we want stable quantum states for us to manipulate the qubits. We don't want the quantum states to be disturbed. So there were 2 hyperfine ground states that were generated, and these states were used to represent the 0 and the 1. They recorded a pretty good. They got some pretty good results here. So they say that the superposition state had a coherence of about 50 seconds, which is a long time for a particle to be able to be contained in this purely quantum waveform state. They did about 150,000 qubit preparations and readouts, and from those 150,000, they got an error rate of 0.07%. So that's a really good error rate. When they read out a qubit state, if it shines, the state equals 1. If it doesn't shine, then they interpret that as a state equals 0. And as you see, here's the laser cooling in all different directions, the magnetic field, the DC electrodes, and these would be the ones to generate the oscillating magnetic field. So there's a lot of future advances that remain. There's many technical difficulties like maintaining the quantum coherence, scaling up to more entangled qubits, and the development of the algorithms. There's a paper on physics.org of November 29, 2017. They set a new record for about 10 entangled qubits, and the price has to go down because right now, I guess it's about $15 million for a D-Wave quantum computer, so they have to make that more affordable. So that's it. Thanks.